So my name is Trisha Spanbauer, and I'm going to be the presenter for the Paleoecology group. This is sort of a boring slide, but I can assure you that none of these folks are boring people. It's been a great past couple of months getting to talk about science with this great group of people. I also want to recognize Jacqueline Gill, who was the co-chair of this group along with myself. Okay, so just a brief overview of what this talk is going to include. At the beginning, just a bit of introduction about paleoecology. Then I have 6 questions that really drive what our group talked about, the essential questions that we see as sort of where the field is going, where it's been, and where it's going. Okay, so continental sedimentary records provide long, continuous, unweathered samples. This is essential to a lot of questions in paleoecology and evolution, is this continuous record of change. And we look at all sorts of different proxies, from biological proxies to chemical proxies. And these observations provide holistic insights into dynamics of evolution of organisms and ecosystems over time. And I want to highlight some of the emerging proxies that have come on the scene over the last couple decades, including ancient environmental DNA and biomarkers. The real power of these emerging proxies is when they're paired with more traditional proxies such as fossils and pollen to create a more complete picture of biodiversity in the past. And then I wanted to talk just briefly about ancient lakes. Some drilling records have been discussed from ancient lakes through conversations today. I brought this diagram in to highlight some of the past species in ancient lakes conferences, because it highlights some of the ancient lakes that have been drilled through time here in the blue arrows, but also pairs that with emerging technologies in geosciences, so the red arrows, or molecular techniques, orange, and then areas of research that have been important to thinking about ancient lakes, like anthropogenic threats. And why ancient lakes? There's a high level of endemism in these systems, and understanding how that came to be, why there's such high biodiversity, has been an area of ongoing research for the paleoecologists. Certainly not the only one. We had a lot of deep time members in our group as well, so it was nice to look at biodiversity across scales between these types of systems. And so now I'm going to go into those 6 questions we kind of arrived at after winnowing many, many questions. First being, what are the patterns and drivers of biological diversity through time? A classic. It's still with us because we don't fully understand the processes that give rise to biodiversity in the past. And I'm so glad that we just had a talk that showed all of the different marine cores that have been collected, because this classic Sapkowski curve shows mass extinctions, and this is all derived from marine families. And so our knowledge of big mass extinctions is primarily driven through marine events. Okay, so here's sort of the background. What have drill core records shown us? This is a composite of drill cores and outcrops from the Neotropics, shows maximum diversity in the Eocene, about 52 million years ago. Some of the drawbacks of this record is that it's not really the Amazon, that sort of hotspot of biodiversity. It's in the Neotropics, but in Colombia and Venezuela. We're missing the last 20 million years. And there wasn't really paired climate records to go along with this. And this is really sort of what drove the Trans-Amazon drilling project, which just successfully was completed. A 2,500-mile transect through the Amazon that had 2 drilling locations of 900+ meters of core, with another section in the middle of that transect that was assisted with industry partners. And so this is just some of the research kind of moving forward, and the reason and the drive for it is to better understand sort of that biodiversity through time and how that got collected in the tropics. Okay, so Our second question was, how are populations, species, and communities affected by climate change? So that was a good intro, the last 20 minutes of discussion. This is the most recent reconstruction of temperature through time. I really enjoyed this paper's database that it was based on. It was called Fantastic. It's the Phanerozoic reconstruction of temperature, highlighting those extinction events. And so we had a lot of discussion in our working group about just how our community is changing. I bring in one example from Lake Titicaca. This is actually at the population level, where we have an endemic diatom that is dominant throughout a 400,000 year record, but has trait dynamics that change pretty wildly through time. So here, diatom valve size is on the y-axis and time is on the x-axis. What's really interesting is that we get to trace that trait dynamic, start to model the evolutionary behavior, and then more recent work has focused on the adaptive landscape that is operating underneath that trait variation. Okay, so moving from climate to tectonics, like textbook stuff here, right? Like allopatric speciation arrives from having populations separated by some sort of usually barrier that arises from tectonic activity. And so here's Humboldt's classic description of biodiversity by elevation. And so to show a little bit about what drill core records can provide, here's an example from Lake Malawi that has both climate and tectonic drivers that set up different states within the lake system. This blue deep water state, as well as a green lake conditions. And that alternation is hypothesized to give rise to speciation and radiations within the cichlid groups there. Okay, so disturbance on the landscape and through time definitely has an impact on biota. And our group kind of focused a lot on fire as one of those types of disturbance, but it doesn't have to just be limited to fire as a factor in what drives these communities and populations. Here we have a really nice record of deep time fire. A lot of the group that we worked with had some experience with Lake Quaternary fire that has the combination of being driven by humans and temperature. Here you can see that there's lots of drivers in deep time that allow for pretty massive fires to set up. And so bringing it to a drill core record, this is an example from Lake Malawi, in which they collected charcoal as well as pollen, and then had some climate drivers reconstructed as well to set up sort of a history of fire in the region. So some 400,000 years ago, there was a humid period, then a drier period, and fire set up in about 85,000 to 60,000 years ago, when you had the combination of fuel and people in the landscape. Which brings us to humans and the human factor, and looking at what the relationship is between Earth system change and human evolution and dispersal. So this first diagram is fairly high level. We have 5 million years, and then periods of unstable climate, coupled with migrations and technological innovations. You can see sort of the patterns that start to emerge between unstable climate and people moving around the globe. So drilling in a little bit further, no pun intended here, we have the relationship between behavioral transitions, cultural innovation, and phases in modern human origins mapped out along with paleoclimate, and to see sort of how those things co-evolved on the landscape. And then finally, we have how have biogeochemical cycles influenced climate and biodiversity? And so bringing back that Sikorsky curve, what we have with that here is the net sediment flux to the ocean. This has been modeled, and not surprisingly, those curves are pretty tightly correlated. And that makes some good sense, right? Sediment's going somewhere and it's impacting organisms in the systems that that sediment is headed towards. Another sort of recent paper that kind of combines a lot of the different drivers I've been talking about is focused on the end Permian, and focuses on this idea of mega El Nino events. So you can see that here in this tipping point. And then what happened was increased wildfire, had a change in vegetation. That change in vegetation pushed sort of the landscape dynamics. There was much more sedimentation. And then you can see this sort of lag event where you have impacts to the marine environment, both reef impacts as well as impacts to plankton. I bring this particular example in because it combines lots of the multiple drivers I've talked about through these 6 different types. And it also sort of alludes to the fact that we need everybody in this room to reconstruct paleo-environmental change. Okay, so now the needs. And this echoes a lot of what everybody said already, but I will highlight in various categories what our group really landed on as the most important things. And so, modular platform for deep drilling in areas that are covered in water. And usually it's big water that has lots of wave action and it's very deep. And so it has to be a platform that can sustain long stringers for and drill crew for big operations to reconstruct massive amounts of time. And then I will echo what Cody said, mobile laboratories that can support clean work is really important to a lot of the emerging proxies that are becoming more common in some of these drill core records, like ancient environmental DNA. And then these are already supported, but I want to just underline how important they are to be supported, and that's the increased support for infrastructure and project development and management. There are only so many folks at CSD, and there's a lot of work to be done for any number of PIs on some of these very complex and long-term projects. And then pilot and site development resources to make sure that we're getting to drill in some of the best spots. Okay, so after we have the core, what's next? It's hard to coordinate everybody who works on a project to get their proxies evaluated in the right order, right? Like age models need to be created before you can really well constrain events, or perhaps people need to access cores prior to other subsampling. So it's really logistically complicated to make sure that everybody is getting their resources post-coring at the right time, and that funding comes at the right time. And then we have that all the data streams that are coming in, right? We have a lot of data systems that are set up for core description and logging at CSD. Then we have everybody at individual labs creating data sets. And then we have data sets that get deposited. And to coordinate all of that requires interoperability between all of these different organizations that are listed here. And then just to end with needs for engagement and community building. I'm sure lots in this room have had the opportunity to participate in workshops that gave them the training to do the work that they do. And so continued support for that is of top priority. And then there was some discussion in our group about creating some community resources for best practice in safety and field operations. There's tons of documentation out there, but a way in which we can share it and make sure that we are keeping current with the best practices. And then finally, guidance for fair and care principles, especially when partnering with Indigenous communities. There are some organizations within the US that help to do that through like local context, but just to increase sort of working with care principles. Okay, so what's next for our group? We are working on a manuscript right now This is an opinion piece highlighting how drill core records are a really valuable resource to answering fundamental questions in ecology and evolution. The target for this is trends in ecology and evolution, because we want to target an audience that might not know about drill core records and what sorts of information they contain. And then we want to make sure that we are emphasizing the integration of multiple disciplines to address some of these questions that I've shared with you today. I'm happy to take any questions, but I also know that there's some folks in our group who are here today. So